Pluto is an intriguing and enigmatic world that lies beyond Neptune within the Kuiper Belt. Although it was once considered the ninth planet in our solar system, in 2006 it was reclassified as a dwarf planet. From the beginning, Pluto seemed out of place. Its orbit intersects that of other planets, which is uncharacteristic of a planet. However, this has not diminished interest in this remarkable celestial body. As we explore beyond Earth in search of life, Pluto emerges as an intriguing and possibly promising subject, traditionally not considered a location conducive to life. Recent discoveries on its surface and beneath its ice shell have exceeded our expectations. Stunning images captured by NASA's New Horizons mission in 2015 and other observations are challenging our previous perceptions of Pluto, revealing it to be much more than just a dwarf planet. These discoveries have puzzled scientists because they do not fit with what was previously understood. As we delve deeper into Pluto's hidden secrets, we are confronted with questions about the scale of this forgotten world in comparison to Earth. Is Pluto as small as 1 to the power of 3, 4, 5, or 6 relative to Earth? This questioning invites us to reflect on the true nature and scale of Pluto in the cosmos. The theory of the existence of a liquid ocean beneath Pluto's frozen surface has gained support due to the presence of extensional fractures and the lack of significant craters in certain areas, suggesting more recent geological activity than expected. This idea is not new. It has been discussed since 2006 in scientific publications speculating on the possible existence of subsurface oceans on several celestial bodies beyond the gas giants, including Pluto. However, the arrival of NASA's New Horizons mission in 2015 provided new details and stunning images that further fueled these speculations. When the probe reached Pluto, it offered the first detailed view for scientists of one of the solar system's most enigmatic objects, revealing a surface marked by a network of fissures, ice volcanoes, and a huge heart-shaped basin. These discoveries have led some scientists to believe that even more surprising phenomena may be hidden beneath the surface. For example, analysis of the images revealed an icy basin called Tombaugh Regio, located in a position almost exactly opposite Pluto's largest moon, Charon. Although this could simply be an accident, the odds are low. Only 5% of models suggest that when this basin formed, there may have been a subsurface ocean that played a role in shaping it. Later, nitrogen gas present in Pluto's atmosphere cooled and solidified in the frozen basin, and the accumulation of additional water and ice generated a heavy load that tipped Pluto into its current alignment. The notion of an ocean beneath the surface has been a persistent idea, but images of Pluto's far side have strengthened this theory. Strong evidence has been found, including a feature called chaotic terrain, which consists of rich cracks and disorderly plains. This terrain is found on the opposite side of Pluto from the basin known as Sputnik Planitia. Scientists have observed similar phenomena on Mars, Mercury, and Europa, one of Jupiter's moons. At these locations, the collision of an asteroid or comet is suspected to have generated seismic waves that converged on the opposite side of the body, causing effects similar to the chaotic terrain observed on Pluto. Alden Denton, a graduate student in planetary geology at Purdue University, simulated how an asteroid impact could send shock waves through the dwarf planet. These simulations presented a scientific coherence suggesting that such a collision would only have been possible if Pluto had a liquid ocean beneath its surface. Oliver White, a planetary scientist at the SETI Institute in California, conducted a geologic map of Pluto but did not participate in the simulations. Although the features observed on the far side appear similar to others seen in the solar system, the low resolution of the images leaves uncertainty. Nonetheless, there is a consensus among scientists that Pluto has geological peculiarities, particularly a large number of cracks on its far side, which suggest the possibility of a hidden ocean and shed light on its potential origin. Theories about Pluto's ocean have long suggested that it was once a frozen ocean that melted under the heat provided by radioactive elements in a rocky core. In this scenario, when the ice melted and refroze in the cold basin, wrinkles formed on the surface, similar to the wrinkles that appear on an apple left in the refrigerator. These wrinkles would have originated due to the contraction of ice as it melted and the expansion as it froze, creating cracks in the surface. If this theory is accurate, images of Pluto should show older wrinkles and more recent cracks. However, the images from the New Horizons mission showed mostly cracks. suggesting that Pluto's surface oceans may have started out as liquid and then eventually froze. Observations from the New Horizons probe revealed a giant rift running across the near side of Pluto, appearing to extend from the North Pole toward the South Pole. This feature, known as Pluto Rift, does not indicate a sudden change in the surface but is more likely a mark left by the continued expansion of the frozen ocean. The presence of water on Pluto is also suggested by observations of water on the near side of the planet, which shows signs of being impregnated with organic molecules. Although it may seem unlikely on a world like Pluto, laboratory experiments have shown that solar and cosmic radiation can create complex organic compounds, including bases present in RNA and DNA. These findings reinforce the theory that Pluto could harbor organic molecules and potentially support life. In addition, the probe's observations revealed a red band at Pluto's equator, possibly composed of organic material, corresponding to a region with greater solar exposure and warmer temperatures. This finding is significant because it indicates the presence of liquid water and organics on Pluto, two key ingredients for life. On the other hand, some UFO hunters have suggested the presence of artificial structures on Pluto, pointing out anomalies in images of the dwarf planet, such as a smoky trail visible on the surface. Although NASA attributes this anomaly to natural phenomena, some believe it could be evidence of extraterrestrial life on Pluto. Pluto, often dubbed as a planet of contradictions, continues to captivate astronomers and enthusiasts alike due to its complex nature. One of the most striking aspects of Pluto is its atmosphere, which, despite its great distance from the Sun, is dynamic and ever-changing, composed primarily of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere undergoes seasonal changes, expanding and contracting as it orbits the Sun. This phenomenon is reminiscent of the seasonal cycles seen on Earth, although they occur over a much longer timeline given Pluto's 248-year orbital period. During its closest approach to the Sun, Pluto experiences an increase in temperature, which causes nitrogen ice to sublime into gas, thickening the atmosphere. As it moves farther away, the cold temperatures cause the atmosphere to freeze back onto the surface, leading to a drastic reduction in atmospheric pressure. This cyclical behavior provides valuable insights into the processes governing icy bodies and may serve as a model for understanding similar phenomena in distant exoplanets. Another noteworthy feature of Pluto is its varied surface geology, which showcases a mosaic of terrains that speak to its geologic history. Observations from New Horizons revealed regions characterized by smooth plains, towering mountains, and deep valleys. The region known as Sputnik Planitia is particularly fascinating. It features vast nitrogen-rich plains that display polygonal patterns thought to result from convection within a subsurface ocean. These patterns suggest ongoing geological processes, hinting at a world that is far from being geologically dead. Pluto's mountains, some rising as high as 3,500 meters, are primarily composed of water ice, which behaves like rock under the frigid conditions of the dwarf planet. The presence of mountains indicates that Pluto has experienced tectonic activity, possibly driven by the internal heat from radioactive decay or the freezing and thawing of subsurface oceans. This geological activity contrasts sharply with the prevailing notion of a static, unchanging world and suggests that Pluto is a dynamic body with a complex history. The presence of methane on Pluto's surface is also of great interest. Methane ice can create a diverse range of colors and features, adding to the visual complexity of Pluto. Scientists believe that the interactions between methane and ultraviolet radiation from the Sun can lead to the formation of complex organic compounds. This raises intriguing possibilities regarding the prebiotic chemistry that might occur on such distant worlds, highlighting Pluto's potential as a subject of astrobiological study. Moreover, Pluto's relationship with its moons, particularly Charon, adds another layer of complexity to its characterization. Charon is so large relative to Pluto that they are sometimes referred to as a double system. The gravitational interaction between the two bodies results in a synchronized rotation, meaning that Pluto and Charon always show the same face to each other. This unique relationship influences the orbital dynamics and may play a role in the potential geological processes on both bodies. Recent studies have suggested that Charon may also harbor a subsurface ocean, further complicating our understanding of the system. The gravitational pull from Pluto could generate enough heat within Charon to maintain liquid water beneath its icy crust. Such discoveries would imply that both Pluto and Charon may share a common history of geological activity and potentially even organic chemistry. The scientific community is continually refining its understanding of Pluto, and future missions may shed even more light on this distant world. The ongoing analysis of data from New Horizons has prompted discussions about additional missions to the Kuiper Belt, where other similar objects could provide comparative insights. Objects like Haumea and Makemake, which share characteristics with Pluto, could yield valuable data regarding the formation and evolution of the solar system. The implications of understanding Pluto extend beyond its own boundaries. Studying such distant worlds can inform theories about the formation of planetary systems, including our own. By examining the similarities and differences among these celestial bodies, scientists can develop a broader perspective on the processes that govern planetary formation and evolution across the universe. Pluto's intriguing composition, including its potential for organic molecules, leads to speculation about its capacity to support life. While the extreme conditions on its surface may seem inhospitable, the possibility of subsurface oceans offers a glimmer of hope. Such environments could harbor microbial life similar to extremophiles found on Earth, which thrive in harsh conditions. If life does exist in these hidden oceans, it could fundamentally alter our understanding of life beyond Earth. Cultural perceptions of Pluto have also evolved over the years. Once viewed as a ninth planet and a symbol of hope for discovering new worlds, its reclassification to a dwarf planet sparked debates within the scientific community and the public alike. This shift has encouraged broader discussions about what constitutes a planet and how we classify celestial bodies in our solar system. Pluto's story serves as a reminder of the dynamic nature of scientific understanding and the importance of revisiting and refining our definitions as new discoveries are made. In conclusion, Pluto stands as a beacon of intrigue within our solar system, challenging preconceived notions and inviting ongoing research. From its complex atmospheric dynamics and geological features to its potential for harboring organic molecules and subsurface oceans, Pluto embodies the mysteries that lie beyond our immediate grasp. As scientists continue to study this fascinating world, each revelation brings us closer to understanding not only Pluto itself, but also the fundamental questions about life and the nature of the universe. The journey of exploration continues, ensuring that Pluto will remain a subject of fascination for generations to come. Pluto's unique characteristics have led to intriguing scientific inquiries and theories, particularly regarding its formation and evolution. One of the compelling aspects of Pluto is its potential to host cryovolcanism, which is the eruption of substances like water, ammonia, or methane instead of molten rock. The presence of large smooth plains and towering mountains suggests that some geological processes may involve the release of these materials from beneath the surface. The possibility of cryovolcanoes challenges traditional notions of what constitutes volcanic activity and expands our understanding of geological phenomena beyond Earth. Moreover, the detection of various surface features raises questions about Pluto's climatic history. Scientists have noted that Pluto's surface is dotted with bright and dark regions, indicating diverse chemical compositions and geological processes. The bright regions are predominantly made of nitrogen ice, while the darker areas contain complex hydrocarbons that may form through photochemical reactions driven by solar radiation. These findings underscore the intricate interplay between sunlight, surface materials, and atmospheric conditions, inviting further study of Pluto's climate dynamics. In addition, the exploration of Pluto's atmosphere has significant implications for understanding planetary atmospheres across the solar system. The atmospheric pressure on Pluto, although extremely thin, has shown variations that could be linked to seasonal changes. This behavior may parallel atmospheric dynamics observed on larger bodies such as Mars and could provide insights into the atmospheres of exoplanets with similar characteristics. The ongoing research surrounding Pluto also highlights the importance of interdisciplinary collaboration. By combining insights from geology, atmospheric science, and astrobiology, researchers are piecing together a more comprehensive picture of this distant world. As technology advances and new missions are planned, the prospect of discovering even more about Pluto's secrets remains tantalizing. Each new piece of data has the potential to reshape our understanding of not just Pluto, but also the broader context of icy bodies in the solar system and beyond.